Introduction to Electrodynamics by David J. Griffiths, problem number 2.11. In this problem, we have to find E field inside and outside a spherical shell that have a radius r. And this spherical shell carries a uniform surface charge density called sigma. And then after calculation, we have to compare our results with problem number 2.7. So consider a spherical shell having a radius represented by capital R. And on the surface of this spherical shell, charges are uniformly distributed, called surface charge density. First we have to calculate E field inside this spherical shell. So we consider a Gaussian symmetry in the form of concentric sphere having radius small r. If you notice from figure, for inside small r is less than capital R. So to calculate E field we use integral form of Gauss's law, that is according to integral form of Gauss's law, that is close integral E dot dA equal to Q enclosed over epsilon naught. As you see from figure, Q enclosed by inside this spherical shell is 0 because charges are distributed on the surface of this spherical shell. So Q enclosed equal to 0. So our E field will also be 0 because Q enclosed by this surface is 0. So E inside is equal to 0. Now we have to find E field outside this spherical shell. So to find E field outside this spherical shell, we imagine a Gaussian surface in the form of concentric sphere having radius represented by small r. Here forget this radius and just remember this radius. So for outside small r is greater than capital R. To find E field outside this spherical shell, we again use integral form of Gauss's law, that is equal to close integral E dot dA is equal to Q enclosed over epsilon naught. Here our first task is to calculate Q enclosed by this surface, that can be calculated from uniform surface charge density sigma, that is equal to sigma equal to charge per unit area, and from here Q enclosed equal to sigma into A. Here A is area enclosed by this spherical shell, that is equal to A is equal to 4 pi r square, because from center to this surface we have radius capital R. We just put this relation into this equation and we get Q enclosed equal to sigma into 4 pi r square. We just put this relation into this equation and we get close integral E dot dA equal to 4 pi r square into sigma over epsilon naught. And in this equation, as we know that dA is a area vector and it is always normal to the surface. So if we consider this is a small patch of this spherical shell, then charge enclosed by this patch is Q and area vector of this patch is pointed in this direction called dA. And we also know that E field due to positive charge is pointing radially outward, so E field also pointing in this direction. And from here angle between dA and E field is 0, so we can say that theta is equal to 0 in this case. So by taking dot product of this relation, we have close integral E dA cos of 0, as cos of 0 equal to 1. So this is equal to close integral E dA, and this can be written as E close integral dA, and this is equal to 4 pi r square sigma over epsilon naught. And here dA is a area of spherical shell that is equal to 4 pi r square. But here we talk about this spherical shell. So for this spherical shell, we have radius is a small r. So we just replace capital R with small r, and we just plug in this relation into this equation. And we have E 4 pi r square equal to 4 pi capital R square sigma over epsilon naught. And from here 4 pi will cancel with 4 pi, and we have E is equal to capital R square sigma over epsilon naught small r square. That is E field outside this spherical shell. And if we talk about vector form of this E field, we have just E vector and R unit vector. So this is a vector form of this E field, and this is always directed radially outward. Now we have to compare this result with the problem number 2.7 results. So recalling problem number 2.7, in problem 2.7, in problem 2.7 we have E inside equal to 0. So in previous problem we have also E inside equal to 0. And in problem 2.7, E outside equal to 1 over 4 pi epsilon naught q over r square into r unit vector. This is a E field outside in problem number 2.7. So we have to just reduce this relation into this equation by using uniform surface charge density relation. So recalling uniform surface charge density relation, sigma equal to charge per unit area. From here we know that area equal to 4 pi r square, so q over 4 pi r square. As we discussed, we take radius of this sphere, that is capital R. So by rewriting previous result, E equal to R square sigma over epsilon naught R square into R unit vector. We just put this relation into this equation. So we have E is equal to R square over epsilon naught R square into Q over 4 pi R square into R unit vector. R square cancel with R square, so we have E equal to 1 over 4 pi epsilon naught Q over R square into R unit vector. That is exactly equal to this relation, but here is a difference. We calculate this relation by using Coulomb law, and we face some difficulty, but if we use Gauss's law, then we easily calculate E field due to charges. So we can say that Gauss's law is more general than Coulomb's law.